So, as I said last time, we did so far combinatorial circuits. We showed you how to implement them using different, approaches, normal gates, just NAND gates. You should know as well how to use just NOR gates, multiplexers, ROMs. Of course, this is about combinatorial circuits. So the components that we covered so far can be used in combinatorial circuits. We have the second part where we need to talk about sequential circuits, and of course we need to cover some components. But before we start the sequential circuits, as I said last session, in the labs you will need to use now another implementation approach. I mean, instead of using the ICs and the breadboard, we will switch to FPGAs. So we need to cover FPGAs first in the lecture for you to be able to conduct the labs. So half of the labs will be on FPGAs, half of the labs are on breadboard and the ICs. So today I'm going to talk about briefly about FPGAs. What is an FPGA? How do we use it? And then we will start a VHDL as well. So VHDL is a hardware description language. In order to use an FPGA, you need to use a hardware description language. You need to describe your circuit. So this is different from C, is different from it's not a programming language, it's a hardware description language. All right, so as you can see from the title, we have two parts. So the first part is FPGA briefing, so an introduction to FPGAs. And again, what I'm going to cover here is for your information. And of course, there are things that are good for you to learn, to know. You may not use them, but are always good for you to know. And you will see that there is a software tool that we are going to talk about some steps here. And you will see that most of the steps will be done by the software tool. So for you as designer, you have to make sure to write a good description, a correct description, like when you write a code in C. So you just worried about writing a correct code that does what you want, and then the rest is done by the software, and you run it, and then you test it. So it's very similar here. You have to make sure that you write a correct description of your code. So if you want to describe an AND gate, you should write the code. It should be the description. There should be no syntax errors in your description. And then when you test it, it should work as an AND gate, not as a different gate. So we can do simulation as well to make sure that this is correct. Right, so I will talk about the FPGA briefly. So what is an FPGA? FPGA stands for Field Programmable Gate Array. It is a silicon chip. So it's a chip that is programmable. This is very important. And this is one of the main advantages of using FPGA. So you can go and buy this chip. You can add it to your circuit, and then you can configure it. So as I said last time, I gave you a simple example. You can configure it to act as an AND gate. And then you can change your mind later on, and you can describe a different one, an OR gate. You remove this and you change it. So it's programmable. This is what we mean by programmable. So you can change your circuit whenever you want. And this is a very big advantage. So the FPGA is made up of an array of logic blocks or logic elements. We call them as well. In some books, you will see logic elements, or in the literature, you see logic elements. An array of millions of those logic elements. So it includes millions of those. We are not talking about tens or hundreds. We are talking about millions. So the blocks can be configured and connected together to get your circuit. So you may have a circuit that will require one logic block. You may have a circuit that will require 10 logic blocks. So those logic blocks will be connected together to build your circuit. This will be done by the software tool that we will use. I added this slide just to give you an idea. This is a figure of an FPGA here. You go and buy it, and then you can use it. And then we have as well what we call FPGA development boards, and those are the boards that are used, you know, for research, for teaching. So we have an FPGA in it, which we can configure. Plus, you have extra components that you can use to test your circuit. So as you can see here, we have some switches here. We have some test buttons here. There are some small LEDs here. I don't know if you can see them. So there are LEDs here as well. 7-segment displays, extra, you know, pins for you to connect to the FPGA, and so on. So those will help you to test your circuit quickly. So for example, you can describe an AND gate, and then we can configure this FPGA to be an AND gate. And then how do you test it? You can, for example, take 2 switches from here, you connect them, and you take 1 LED from here. There is an LED here, and then you can play with the switches and you test your AND gate. And this is what you will use in the lab. This is the board that you will use in the lab. You see the FPGA here is from Xilinx, and the one that we have here is from Altera. So there are different, vendors, FPGA vendors, and you will see that Xilinx and Altera, they share most of the market. In the past, I mean, if you go 4 years back, we used development board with Xilinx FPGA, and now we switched to Altera. But again, the concept is always the same. The code that you write to configure for this will work on both. It's standard. So VHDL is a standard. It's like C. It doesn't depend on which processor you are going to use or microcontroller that you are going to use. It will work because it's a standard. Is this clear? So this is the FPGA. We have, if you go now and talk about, you know, implementation approaches, you know that the first 2 here that I put are, you can consider them as soft. And this one is hardware, hard. What I mean by software, so we can have a microprocessor or microcontroller, and we write a code for it. We just write C++ code or C code or whatever language we use, and then we just run it on. So the code that we write are the instructions for this microprocessor or microcontroller to be executed, and that's it. We don't need to worry about the hardware. We don't need to know what do we have inside this microcontroller or microprocessor. We have as well the GPUs. By the way, microcontrollers, we will use them in the next course. Embedded systems. Microcontrollers are mainly used in embedded systems. So this will be the main processing unit for our case. Right.
Victor?
Yes?
These are hardware or?
Pardon?
This microprocessor, this is all hardware, yeah?
No, we are talking about the implementation approaches. At the end, we are using hardware in all solutions, but once you have a microprocessor or microcontroller, you don't need to worry about, of course, the microprocessor, microcontroller, it consists of, you know, the components that we described before in digital, combinatorial circuits, and of course it has as well for sequential circuits. So it's a big digital circuit, but we don't worry about what do we have inside this microcontroller. We just write a code. So it's software approach. Software, you just go and write the code, and that's it. This is all what you need to do for the microcontroller to work. So those are software. Same for GPUs, the graphics processing unit, and those are mainly for graphics. So we just go and write a code. And this is what I mean by those are software approaches. The other ones, hardware approaches. You can do the same with what you do with a microcontroller, microprocessor. You can do it on an FPGA. But the FPGA comes empty. You need to design your circuit. You need to describe your circuit yourself. Or you can go for specific integrated circuits, which what you do, you bring ACs and you put them together and you can get a PCB at the end and you work with it. So this is what we mean by hardware. So you need to do the hardware yourself. The other one, you have the hardware, you just you write the code, the instructions, because the hardware on its own will not work. If you bring a microprocessor, it will not work unless you write a code and you run it on it. This is what I mean by software and hardware. So you have different applications. What you can do with a microcontroller, you can do it with an FPGA, or you can do it with an ASICs. So you can design your circuit. Now, of course, our focus is not on the software parts, it's the hardware. So the hardware approaches. So which one, as designer, you should go for? Of course, there are different advantages and disadvantages for each one. The main advantage if you go for FPGA is, as we said, the reconfigurability, or they are programmable. You can reconfigure them to get a different circuit. It's a low development cost and short time to market because the FPGAs are not that expensive, and you can get the circuit on it quickly. It's in a short time. For someone who's good in VHDL, in a hardware description language, you just describe your circuit quickly and you can get it onto the FPGA in very quick, which is not the case for ASIC. ASIC, it requires time. It requires time for testing, to select the component, to make sure that it works, and so on. So there are lots of steps for you to, and then, but ASICs, once I'm talking about, companies, I mean, for example, they do those devices, they can, if they go for ASIC, of course, they need to do to produce them in high volumes, yeah. And usually when we produce in high volumes, it will be in lower cost compared to FPGA. And low power as well. They don't consume as much power as the FPGA. So it's always a trade-off. It depends what you want to do. It depends how many devices you want. It depends on everything. There are many aspects that you need to consider to choose FPGA or ASIC. You need to learn both of them. So this is what we are doing. So the FPGA vendors that we have, I mean, you can find in the market, we have Xilinx, Altera, Atmel, Latest Semiconductor. As I said, Xilinx and Altera, they share over 60% of the market. There were in the past as well, the technology used to manufacture those, FPGAs. We have the SRAM based and the flash and anti-fuse. Flash and anti-fuse is not used anymore. And of course, I'm not going to enter into details for this one because it's out of the scope of this course. The recent FPGAs are SRAM based FPGA. So this is technology used. And again, it's out of the scope to talk about this, and this will not benefit you at this stage. So now, what do we have inside the FPGA? This figure shows the traditional FPGA structure. So we have a matrix of programmable logic blocks or logic elements. So those are that we have here. I'm going to do those in gray, and now I'm writing in red here on top of them. So those are the logic elements, logic blocks. We have millions of those in a circuit, in an FPGA. And then we have input-output cells, which connect the logic cells to external signals. So those cells here. And of course, we have lots of those cells. Those are used because the FPGA is a chip. So we will have inputs and outputs. So we can have inputs and outputs. So those will be connected to the inputs and the outputs of the FPGA, the pins, the input-output pins of the FPGA. And then we have the programmable routing network interconnecting the cells. Those lines that you see here between the cells. So for example, if I'm going to do a simple circuit, an AND gate, the AND gate may require, for example, just one logic cell. In this case, we don't need to interconnect anything. But if you have a circuit that will require 4 logic cells, so those 4 need to be together. So those connections will be used between the cells. Oh, so there will be like basically wires connecting the cells together or connecting the components that will be implemented in the cells themselves. Right? So in this case, those cells will be connected. Is this clear? Again, all this will be done by the software tool. I'm just explaining, what for you to know what's happening when you click on a button in the software tool, or when you click on the menu and run something, you know exactly what's happening. So you don't need to worry about this, how the connections will happen and so on. Now, if we go inside a logic element, which is the main block in FPGA. So inside this logic element, we have some components. And the main component is this 4 input LUT or lookup table. So this is the main component, 4 input lookup table. In some FPGAs, and especially the recent ones, you can find it even with 8 inputs. So it depends on the FPGA, but we are just talking about the, like the standard one. I mean, we can, most of them, they have 4 inputs and 1 output. And then, as you can see, there is a multiplexer and there is flip-flop. We didn't talk about flip-flops yet, but flip-flops are used in sequential circuit. So there is a component that is used in sequential circuit, and the rest are used for combinatorial circuits in one cell. The LUT, which is of course, we will talk with more details about flip-flops in the next topics. So for now, just you need to understand that this is used for if you have a sequential circuit, then those will be used. The LUT, which is, as I said, the main component in the logic block or the logic element, can be used to implement any logic with 4 inputs. So for example, if you want to implement a NAND gate, this one LUT will be enough, because this LUT can be used to implement any input with 4 input, any logic with 4 input and 1 output. If you have this circuit that you want to implement, and you can see it has 1, 2, 3, 4, 5, 6 NAND gate and 2 NOT gates. Again, this can be implemented in 1 LUT, as it has 4 inputs and 1 output. If you have now a circuit that includes 8 or 10 inputs or more, of course, more LUTs will be combined together and used, as I explained in the previous slide. So we can have 2 blocks together, we can have 4 blocks together. I don't know who has his mic not muted, so can you please mute your mic?
Doctor?
Yes.
So inside the 4 LUT, there is not AND gate.
Pardon?
Inside 4 LUT, there is not AND gates.
Sorry, there is not. What? I didn't hear you well.
There is circuits inside 4 LUT. There is circuit.
The LUT can be
Yeah.
used to implement any circuit, combinatorial circuit, which has 4 inputs and 1 output. I just gave you examples here of 2 circuits, 2 simple circuits. One is NAND gate. I don't know who's. I mean, there is a noise in your background. I don't know. Is this a TV or? Can you just mute your mic, please?
No, this is not me.
Right. So, as I said, so it's not this one. I said LUT can be used to implement any circuit with 4. I didn't say it has NAND gate. I didn't say it has AND gates. I didn't say anything. I said the LUT can be used to implement any circuit which has 4 inputs and 1 output. And I gave you 2 examples here. So the examples that I gave you include AND gate, NAND gate. But if you have a circuit like this one as well, this can be implemented in one LUT because it has 4 inputs, it has 1 output, and that's it. This is what I said. Is this clear?
Yes.
So any circuit that has 4 inputs, 1 output will be implemented. If you describe that circuit using VHDL and you implement it on FPGA, it will be implemented on one LUT, which is basically on one logic block, because the logic block includes one LUT. So if your circuit includes 6 inputs and 2 outputs, then of course more logic blocks will be used and interconnected together. Is this clear? So
Yes.
this is what's mentioned about LUT. The LUT can also be used. Do you remember in the previous topic we talked about RAM? An 8 by 1 RAM. What does it mean? How many address lines we will have in our RAM? If I say this, so I have this RAM, how many address lines and how many data lines we will have?
8 address lines.
3 and 1.
It's not 8 address lines.
3 address lines, 1 data line.
That's good, excellent. So we will have 8 memory locations, and to have an address for each memory location, we go from 0 to 7. Then I need 3 here, address lines, and I need 1 because here the data is 1. So I have 1 bit in each memory location, so the data is 1. So those LUTs can also be, so for example, if you need to use a ROM or a RAM, it can be used for both. I put here RAM. RAM is random access memory, but we can work with RAM for now. So you can be used for ROMs. So one LUT can be used to implement 16 by 1. What does it mean, 16? How many address lines we need? We need 4. So those are the 4 address lines, and this is the output, which is 1. And of course, we can have larger memories by combining, LUTs together. So for now, I told you that the LUT can be used to implement any logic with 4 inputs and 1 output. It can be used to implement memories as well, 16 by 1 memories. If we use LUTs to implement memories, we call this type of memories distributed RAM because it's distributed over the FPGA because we have many blocks, right? Why we use this name? Because we have another type of memories that we can have in FPGA. So, and this is what I'm going to talk about. So in addition to here, we talk about this traditional, we talk about the, so we talk about 3 parts here. We talk about the logic blocks, we talk about the input-output cells, and we talk about the network, the routing network. There are other parts in the FPGA, inside the FPGA, but outside those logic blocks. So for example, we can have what we call memory blocks. I didn't present them here. So those can be used as memories only. So if you need in your circuit to use memories, you can use them. You can use those blocks, or you can use the LUTs to be your memories. So the designer have the choice. So if your circuit is too big and you need plenty of storage memory, then it's always good to work with those external memories, we call them block RAMs, rather than using the LUTs, because the LUTs, you will use them for other things. So there are extra components. So for example, as I said, we call them block RAMs. So if I say block RAMs, this means those are the external component memories. external to the logic blocks, but they are still inside the FPGA. Yeah, everything is inside the FPGA. We have as well multipliers, dedicated hardware blocks like multipliers, and you will see later we have a topic about others and multipliers, arithmetic circuits, and arithmetic circuits, they consume a lot of hardware. So of course you can do them using LUTs or logic blocks, and you can use those multipliers which are already there in the FPGA, that you can use them as multipliers only. You cannot use them for something else. LUTs can be used for something else, but those are dedicated blocks. They are already there to be used as multipliers, like an AC that you buy. So if you buy a NAND gate, it can be used as a NAND gate only, and that's it. It's a NAND gate. It doesn't do something else similar to this. So you have multipliers, so it works as a multiplier. And even most recent FPGAs, they have even some small microprocessors on them, tiny microprocessors. They can do some simple, operations, which you can program as well. So in addition to describing your circuit, you can include those microprocessors in your circuit, and you can write the code for them, so to work with your logic. But of course, we are not going to go into this. This needs to be, it's more advanced. And by the way, what we are covering here, I mean, now FPGA and VHDL, a course is on its own is not enough to cover them, because there are plenty of things to be covered. We are trying to give you the fundamentals, and then, of course, you can on your own you can learn, further, and you can learn more by just acquiring the fundamentals. Right, now the FPGA design flow. Once now you go to the lab, you have the FPGA board. What do you need to do with it? How do you work with it? As I said, the first thing to do is to write, is the design entry, is to write the code, the description, your hardware description. So we can use, there are two approaches or two ways. So you can use VHDL, a hardware description language such as VHDL. And by the way, there are other hardware programming languages. So we have VHDL and we have Verilog. Those are the most used ones. And most companies, they use one of them, either VHDL or Verilog. And once you learn one, the other one is straightforward, because there is similarity between them, and it's the same concept. So you just understand the concept. It's like programming languages. Once you learn one, the rest will be easy. I mean, it's just the syntax that will change. I mean, how do you do a loop? How do you do an if statement? How do you do? But the concept is the same. For us, we will learn VHDL, how to use VHDL. So the first step is to write the code. Of course, you will have a software. Each FPGA will come with their other software. You open the software, which we already have it installed. I will talk about it later on. And then you create a project, and then you start adding the files to the project. You add the VHDL file, and you describe your circuit. Of course, you need to follow the syntax of the language. Or you can use schematic. Schematic is connecting, you get components from library and you connect them. I will show you this later on. Or you can mix. You can get components, you connect them, and then you create a component yourself using VHDL, and then you add it to your schematic. So you can always mix. So you can have hybrid, both, which I will show you later on. I don't know if you will do it in the lab, but you can do it. I think we did it in the past. We showed students how to do it. But again, the components that you use from the library, they are described using VHDL. So behind those components is always VHDL. So VHDL is the most important thing for you to learn. For schematic is very easy, just connecting. It's like when you do simulation for bit circuits with components, it's exactly the same. Right. So this is the first step, writing the code. And then the next step, and again, the steps that we are showing here are using the software tool. We need to do what we call synthesis, and this just one click in the software tool. But it's good to know what's happening when you do synthesis. What does it mean? So your code, the VHDL code or the schematic or the enter design will be synthesized into a circuit that consists of logic elements provided in the FPGA chip. So this code will be like compiled, and then it will be translated into another code that the FPGA will understand, or that the software can use later on. So it's code that will specify, okay, this code is trying to describe this and this, so we can use this number of logic elements. It will select which elements can be used as well, and so on. So this is now it goes into the hardware. The code will be like starting the translation into the hardware. And then the next step, you do the functional simulation. You know, like when you write a C code, you can always debug and check if things are working fine. Now, if you do an AND gate, you describe an AND gate and you want to make sure that it works before you continue the steps, before you go to the FPGA. You need to test it. So you can have, those are the cases. You can have 0, 0, 0, 1, 1, 0, 1, 1. And then you observe the output. So you describe. So what you need to do during this functional simulation is to provide what we call the test cases. And then you observe the outputs that you will get from your design. So this is, you can do it, there are two ways. You can either do it with waveforms like this. So this means this is a 0, this is a 1. So this means my input here is 0, and then it's 1, and then 0, and then it's 1, and so on. And here it's 0, and then 1, 0. So here is 0, 0. Here is 0, 1, 1, 0. And we will have a topic about simulation. So we'll have, so don't worry, now I'm talking in general, but we will have a special topic just on how to do simulation. So you can do, and you will do it as well in the lab. And then you observe the output. So this is what you need to provide to the software. And then the software will return, or the simulator will return the outputs. So, and then you observe the outputs and see if they are correct or not based on your inputs. It's clear, yeah? And then if this is fine, if there is an error, so which means the design is not correct, this is not what you expect, you need to go back to your code and check it, right? So you need to go back and check your code. Now, if the design is good, we go to the next step, or the software tool will go to the next step, which is place and route, or the fitting. We call it the fitting. And this tool determines, so this tool determines the placement of the logic elements defined in during synthesis, during the previous step, the synthesis, into the real logic elements in an actual FPGA chip. You know, when you open the software, when you start a project, you always select which FPGA you are going to use, because there are, from the same manufacturer, from the same vendor, there are different references, there are different FPGAs. So you select which one to use, and based on this, so the tool will know how many logic elements you have inside the FPGA, and then it will map what it have from here into the real blocks of the FPGA. Again, this is done by the tool. I mean, I'm just to let you know what's happening. There are different steps that are happening. And then next you can do timing and analysis and simulation, because we are working with hardware. So for example, if I have this circuit, we will have values here, 0, 0, 0, for example, and then we guess the output X. You see, this output, we will not get it immediately once we have 0, 0, 0. Here we will get this immediately. There is always a delay. Of course, I'm talking about a very, very, very small delay, which as a human, we will not see it. We will see it as it's happening immediately. But there is a delay for propagation of the data from one gate to another. In some applications, it's very important to know how long it takes to get an output, as this output can be used by another block in your design. So, and in this case, you need to do timing simulation to see if you are getting the output at the time that you want or the time that you expect. If not, then you need to go back to your design and repeat the previous steps. There are techniques that will allow you to optimize your design and to work with the you know, to get the what you want. Of course, we are not going to do this. It's a bit advanced. So for us, we will do the functional simulation just to make sure the circuit works fine. Right, and then if the last step, once you are happy with the functional simulation, is just the configuration. So the output from the previous stage, from the place and route, will be what we call a bit file. So a bit file that can be used to configure the FPGA or the configuration file. And of course, the FPGA needs to be connected to the computer, usually using USB, and then you configure the FPGA, and then that's it. You can test the FPGA. Once you configure the FPGA, you can just remove the cable, and then that's it. You have the circuit on the FPGA. Of course, as long as you keep the board powered. Is this clear? So those are the steps. And again, all those steps are done by the, so your contribution or your work should be here in this step, and should be here, simulation. So those are the main steps that we will work. As designer, you have to make sure that your description is correct. I mean, correct, there are no syntax errors, and logically is correct. It gives what we want. And then the rest is done by the software. Right. This is what I was explaining. We have the explanations here in text for you to read. So in the lab, the software tool that comes with this FPGA is the Quartus tool, and of course they have the light edition, which is a free edition that we can use. It's enough for us for this course. You can install it as well in your computer, on your laptop, and you can use it. Of course, we have it installed in the computers lab, and we have this FPGA board as well that you will use. I think the first session, once you start this, the FPGA and VHDL, the first session will be familiarization with the software and hardware tool, and the step-by-step how to use things and so on. So you will see that once you create, you open the software, the first thing that you need to do is to create an FPGA project. And then you need to add files to that project. So the files that can be added can be VHDL, can be schematic. There are other types which we will talk later on about them. For example, when you do simulation, I said you can add a test bench. We call it test bench. So you can add a file to do simulation. So, but this what you need to do in the first step. So you can add VHDL, you can add schematic. And once you add schematic, this is schematic. This is an example of schematic. So we have a library where you can get the components from the library. Do you see them here? So this is an example that I did. So you can connect the components like this, and then you can run and do the simulation. All this you can do it with the software without the need of the FPGA. What you can do as well, you can write VHDL code and do the simulation without the need of any board. The board is for the last step, to configure and to test on the hardware. So for example, let's say that this library doesn't have an AND gate. Of course it has, it's a simple gate, but you may need to use a component that doesn't exist in the library. In that case, you can you add a VHDL file, you describe your component, and then from your VHDL file, you can create a symbol for your component, and then you can add it to your schematic. And this is how you combine both. So you have schematic, you create components using VHDL, you create symbols from the VHDL code, and then you can add them to your schematic and you can test it. So always behind those components is VHDL, is hardware description. And this is what I explained before, if you didn't get the point. Is this clear? Right, that's it for FPGA. So as I said, that's mainly general information, things that are good for you to know and to know how things work. And of course, you will practice. You will. The first lab will be just familiarization, step by step, how to do things with clear instructions. Right. I think it's. I hope you will enjoy it. I think it's something very interesting, and FPGAs are used in many products now. So it's always good to learn those things, yeah. And when I started teaching this course, when I came here, I found out that FPGA wasn't used at all. They were not teaching FPGA, no VHDL, and this was very strange. I mean, digital design with FPGA is like food with no salt. So it's you go to the top ranked universities and check their syllabus. There is always VHDL and FPGA with or hardware description, either Verilog or VHDL with FPGAs. It's very important to do this in digital. Right, now an introduction to VHDL, one of the most used hardware description languages. So today I'm going to talk about the fundamentals, the basics, and then of course we will cover more advanced stuff in the next topics. So today I'm going to explain what is VHDL, and you will see that we will work for VHDL when you start your description of circuit. You need to work with what we call design units. So we'll explain what are those design units. And then, of course, like the programming languages, we have types, data types. We have data types as well for VHDL. We have operators that you need to use with VHDL. So we have, plus, minus, the operators, the normal operators that you use, modulos in C. We have some operators as well. We have similar operators and extra operators in VHDL. And we'll talk about some conventions as well. VHDL conventions. So this is for this first part of VHDL, and of course we will carry on in the next. I think the next two sessions will be VHDL as well. Right. HDL in VHDL stands for hardware description language. So it's a language used to describe hardware, digital circuits. V in VHDL stands for very high speed integrated circuit. So together is very high-speed integrated circuit hardware description language. This started as, a program for the U.S. Department of Defense, and many of the, things they started like that with, U.S. Department, like internet and other things. There were originally programs, in the U.S. Department of Defense. And then it was first released in 1987 for public as an IEEE standard. So it's an IEEE standard, which means, what does it mean standard? So you're right, it doesn't depend on the target FPGA. You can use it for any type of FPGAs. So manufacturers or vendors of the FPGAs, when they design their FPGAs, they have to make sure they comply with this, because it's a standard. So they need to comply. Otherwise, nobody will gonna use their product. Same for microcontrollers. If your microcontroller doesn't work with C, nobody is going to buy it. So this is and the last major revision was VHDL 4.0, which was in 2008. Of course, it is being revised periodically, and of course they get comments, feedback from users, and then they will improve things. Now we can say it's in a stable, very stable now. So it's a technology independent, as I said. It doesn't depend on which FPGA you are going to target or you are going to use. So you can use any FPGA you want with it. Right. So as I said, once you start your design description of your your circuit, we work with units, and those are the two main units that we use: the entity and architecture. And then the other two, I mean, for C, for example, or for C++, sometimes you call the libraries, right? Standard libraries that comes with C++, or even someone can write a library which you can call as well. So we have libraries. For example, if you want to use sine, cosine, you don't need to describe them. You don't need to write those functions. They are already there. You just call the library. Same here. We have components that are already in libraries that you can just use. So you need to call the libraries as well to use those components, which are predefined, defined by other users. And the structure of a library in VHDL, it includes what we call packages. So it's based on what we call packages. So this is, if you want to create your own library, you need to use package declaration and package body to create your library. So I'm going to talk briefly about this. Of course, we are not going to create libraries for our case. We are going to use the standard libraries. We have all what we need from the standard libraries. But it's good for you to know that this is how it works for libraries. If you want to create your own, you need to work with packages. So those are the main design units that we will be using: entity and architecture. So we start with the entity. Right. So if I have a circuit like that, so I have an AND gate here. I have A, B, and C. And let's say that I'm going to hide to color this. So what do you see? So if I'm coloring this, this will be like a black box. What do you see?
Inputs and output.
Good. We can see inputs and outputs, A and B. And this is what you need to do when you start writing the entity. So first thing that you need to do when you start describing your circuit is to describe the inputs and outputs of your circuit. How many inputs do you have? You can always give names to the inputs and the outputs and specify, is it an input, is it an output? And the type. So is it 1 bit? Is it multiple bits? For example, if it's a memory and this is 3, so those are 3 lines. So A is a 3-line bus. We call it a bus. Anything that's more than 1 line is a bus. We talk about this in the first topics, yeah? So you need to specify it as well. So this is what we do in the entity. You think of your circuit as a black box, and you just describe inputs and outputs. Of course, you need to follow the syntax of doing this. How do we do it? All what you see here in this topic in red are keywords, which you cannot use as names for your inputs, outputs, and so on. So for example, I have a circuit. Let's say I'm going to name it Ahmed. I'm giving Ahmed as a name for you to know that you can use any name you want. But of course, it's always good to select a name that has a meaning, that reflects what you want to do. So for example, if you are implementing a multiplexer, it's always good to name it Max or multiplexer or whatever. So something that reflects what you want. And then you start with keyword entity. You give your name. You choose a name for your circuit, and then followed by keyword is, and then ports. So ports, input, output ports are the input and output. And then you open the parentheses and you start listing your inputs and outputs. For example, here I have 2 inputs. So I have A, B, both are inputs. So in is keyword to say it's an input. And of course, all those keywords are defined in the library, the standard library that I'm going to talk about later on. We need to include the library. If we don't include it, nothing will work. I mean, the compiler will return plenty of errors, right? So I will come to this. And then C is an output. As you can see, after each declaration, we have a semicolon here, and then we have a semicolon here, and then the last one, there is no semicolon, and this is very important. And then you close the parentheses and you put the semicolon here. So the last one is after you close the parentheses. And then end
Doctor,
to end your entity, and then with the name. Yes?
why did we write bit after each input and output?
You need to specify, is it one line? Is it 3 lines? I was talking about this in the previous one, right?
So if it's three lines, what will I write? 3 bits?
It's a different name. We call it bit vector. So I'm going to talk about this when we talk about types. For now, I'm just using. So I need to use some of things that we haven't covered yet to give you examples, but I will always try to use simple things. So because you know what is a bit, right? It's either 0 or 1. So if this is just one line, it's a bit. But we have other types, which I'm going to talk about later on, that you can use. So you need to specify the type. So this is the syntax, and this is the general syntax. So you need to give the port name. So the first thing is to give the port name, and then colon, and then the signal mode, is it input or output, and then the type. So this is, we need to follow this. And then we have semicolon, the last one, there is no semicolon. So this is very important to follow the syntax. You don't have to put them in that order, you know, A, B, C. You can start with whatever you want. So for example, I can have it this way. So port, I'm not going to write everything. Yeah, port, and then I can start. You don't need to go to a new line. You can even start from here. So I can have A, or let's start with C as output, bit, semicolon, and then A, input, bit, semicolon, and then B, input, bit, and then I don't put semicolon here. I close the parentheses. You don't need to go to the new line. You can do it this way, and then I'll close it. So it doesn't need to be in order, inputs and then outputs. You can mix. I can do it this way as well, because A and B are both inputs, so you can put them together. A, comma, B, they are both inputs, and then bit. Both are the same type. I can put them together because they are both inputs and both they have the same type. And then I can do C, out, bit, and then I will close, and then semicolon. So this is correct. Both are correct. This is correct. This is correct. Right. So this is for the entity. Now the architecture. I think you can guess what the architecture is used for. The architecture is to go now inside the circuit and describe the relationship between the inputs and outputs. So basically the logic function. So we have, this is, let's say that Ahmed is an AND gate. Our circuit is an AND gate. So, and this is the syntax for the architecture. So we start with the keyword architecture, and then I give a name for my architecture. This is should be different from the name of the entity. And then off, and then here you need to put the name of the entity that you used to link this architecture to your entity. And then followed by is, begin, and then here, and this is the main part of the architecture, you write the relationship between inputs and outputs. So basically, here we have C is equal A dot B, right? If I write it in Boolean algebra. So this is my expression. In VHDL, the equal, we use this operator. We are going to talk about operators later on, but as I said, I need to give you some examples now to understand what we mean by architecture. So this is an operator in VHDL. That means we are assigning A and B to C, and of course we put semicolon. And is another operator that we can use. So and is another operator, and then that's it. I will end
Doctor,
my architecture. Yes.
if we use capital letters or small letters, would it make different?
I will talk about this in the conventions. Yeah. So we'll talk about this.
Okay.
VHDL is not case sensitive, so it doesn't matter. Uppercase or lowercase is the same. But we will talk about this later.
Okay, clear, Doctor.
Yeah. So this is, and then you end and you put the same name that you use for your architecture here again. As you can see here, I wrote and then the lowercase, but here I wrote them uppercase, and this is fine. So it doesn't matter because it will be the same, considered the same. It's not like in C or C++. Right. And this is the general syntax for architecture. Do you see here? I put, in programming languages and in hardware description language, when you use square brackets like that in the syntax, this means this is optional. So you don't have to have declarations. For our example here, we don't need declarations. In some codes or in some descriptions, you may need to declare a constant, you may need to declare a variable and other things. So you put them here. This is the right place to declare them. You cannot declare anything inside the architecture. Between architecture and begin keyword. I will show you an example later on, of course, how with a declaration. Now, if I put the two entities together, this will be in one code. This will be in one VHDL file. So those are together. This is an AND gate. This is a description of an AND gate. But as it is, it will not work. When you compile, you will get plenty of syntax errors. For example, the compiler will not understand what is this, and it will not understand what is this. So we need to add the library. So we need to start to include the library here in the beginning of the code or the description. How do we add library? Of course, we have standard libraries. You can define your library. We add the library by using the keyword library and the name of the library. So the library that we will be using in all the labs, it's basically IEEE library. It's called IEEE. And then, as I said, the library in VHDL is not just calling the library. You have to specify what are the packages that you want to use in your library. So do you remember we said the design units, we have the entity, the architecture, and then we have the package declaration, package body. So if I represent a library like that, the library contains packages, mini packages. So it depends. You may have two, you may have one. So package 1, package 2, package 3, and each part part 1, part 2, and so on. So if this is the IEEE library, it has several packages. You need to specify which package you want to have access to. And then you can even specify which part you want to use. So for example, and how do you do this? By use the keyword use and then IEEE and then dot, for example, package 1. Of course, there are names for each package, and this is available online. All the packages and what you have inside each package is available online. And then you specify which part. Or if you want to have access to the full package, you can just put all here. This means I want to have access to all parts of package 1. And that's it. So by doing this, you will have access to the package. In the labs, we will show you which package that we need to use. We'll show you which library. The library is IEEE, and then the package that you need to use is this one, std logic _logic _1164, and then you can use all to have access to all package. So all the operators that we need to use are defined here in this package. This is what I was explaining about packages. Of course, if you want to create your own library, then you need to create packages first. And creating packages, you need to use the package, the declaration and the package body, which is similar to like entity and architecture. So in the package declaration, you define what you want. So for example, if you need a function, if you need a component, and so on, there are different parts. Again, this is out of the scope of this. We are not going to create our own libraries. We are going to use the IEEE library, which is enough for us. So this is the full code, and this is full and correct code for an AND gate. Now, if let's say that you have this, you configure the FPGA, you have the AND gate. Now you decide to change the AND gate. You just delete this one, this operator, and you replace it with OR. We have the OR operator. I'll just write OR here, and that's it. This becomes an OR gate. Of course, you can change those names. Those are just names, but as I said, it's always good to have a name that has a meaning. So the code will work. It's just a name. It's always good to have OR instead of AND in the names. Is this clear? So you can have as well. So for example, if this is my expression, X is equal A dot B plus C, and we ask you to implement the circuit. So this is the circuit. Then we have OR A, B, C, and this is X. So you just go to, how do you do this? So what do we need to do in the entity? We have A, B, and C. C is an input. So semicolon here, and then we will have X as an output. So X is an output. And then I will just write my code here. X is equal A and B or C, semicolon. That's it. This is my code. So you can use the expression as it is and you write it, and this will give you this circuit. It's very simple. It's not complicated as long as you understand the operators, you understand. So you need to know what is AND, you need to know what is OR. Of course, if you don't know what is an AND gate and OR gate, you will not be able to do this. So you need to think hardware, always hardware. Is this clear? So data objects and identifiers. So identifiers are basically the names that we give to the variables, the input, output ports, your architecture. So those are the chosen names from the user. So we call them identifiers. So you know this. Then the data object that we can use are, like in C, C++, we have constant, we have variable, and we have signal. And this is the most important one here for VHDL, which I'm going to explain later. And we have files as well. File I put here is used for simulation only. So you don't use this to describe your circuit, but you can use it when you want to simulate your circuit. As I told you, we will have a topic about simulation. To simulate, you need to add another code, which is called test bench. And in this test bench, you can use files. And basically, for example, if I want to simulate an AND gate, so I can have 0, 0, I can have 0, 1, 0, 1, I can have 1, 0, I can have 1, 1. I can put those in a text file. Of course, this is very simple. You don't do it for a file. Usually we do files when we have, many test cases, thousands or more of test cases that you need to do. And those test cases can be generated in MATLAB or whatever, and then you can put them into a text file. This text file then you can use, you can declare it and use it. So files are used for simulation only. Now for the description, for the VHDL code, we can use constant variable signals. Constant is very similar to constant in C++. So if you declare a constant, this is the syntax. You need to use the keyword constant, and then you give a name or an identifier, and then the type, and then the value. Constant, you always need to give a value. So for example, if I want to do constant x, and then type, I can call it bit. We will work with bit for now because you know what is bit, it's 0 or 1, and then I give an initial value. And we use this operator to give it. So far we showed you this operator, we said it's equal. And this one is used for equal as well. But you should know which one to use and when. This will depend on the statement that you want to use. So if you are assigning something to a port, we need to use this one. And if you are giving an initial value to a constant or to a variable, we use this one. We will talk about operators as well, and we'll come back to this. So this is the operator that you need to use, and then you give a value. Let's say, and by the way, when we work with bit, we need to put the value between single quotes. We put single quote 0. If we work with buses, as I told you, you can declare buses. We use the keyword vector as well to declare buses. We use double quotes. So if I have a 4-bit bus, if I want to give an initial value, I use double quotes. And then I put the 4 zeros, for example, if I initialize it to 0, 0, 0, 0. So we use double quotes if we have more than 1 bit. We use single quote if we have 1 bit. And then that's it, semicolon. This is a declaration of constant. And then you can use your X inside your code. Wherever you put X, it will be replaced by the value of 0 because it's a constant. Right? Where do we declare this? We declare it between keyword architecture. Do you remember we told you the declaration path? So it will be between architecture and begin. This is where we put this declaration. If you want a variable, it's similar to the constant. And then, so for example, y type bit. I can stop here. I don't need to give an initial value. You may give an initial value to your variable, or you can just stop here. So do you see we put this between square brackets? This means it's optional. You don't have to give an initial value because you can give it later inside your code, inside your architecture. Now you can write y is equal, and then you give the value to the 1, for example, and then you work with y, and you can change the value later on. It's a variable, it may change. If you want to give the initial value, you will do it like what we did for the constant. So you can put here, you add bit equal, and then you give an initial value. Which is the, again, a very important concept here for signal. Signal is basically, you are describing a wire. It models a wire in your circuit. So let's say that I have this circuit. Let's do a simple circuit here. Let's say I have this A, B, C, and then I will have X. So I showed you how you can do it in one line. We did an example, yeah, in the previous slide, how to describe it for your architecture. You can just take X is equal A and B, or C. This is good. This is correct. You can do it. There are other solutions. So if you want to work with signals, so do you see this line? Anything that is not a port, so those are ports, those will go into the entity, right? Anything that is used to connect two components inside your circuit can be a signal. So this one, I can name it S, for example. In my code, I can declare a signal. I can call it signal S bit. Of course, this will be between architecture and begin. So we have architecture, begin, and then I declared my signal. Inside my code, I can write S is equal A and B, and then I can write X is equal C or S. And this is another solution. So you can have all of them in one line. I can separate them like this by having signals. Right? Sometimes you may need to use signals. So for example, if you have, let's say you have inputs like this, outputs like this, Y. So you may need to use this line Y here. So you need to declare this as a signal and then you use it. And both solutions are correct, as I said. Is this clear? So this is what we mean by a signal. We don't have this in C or C++, right? So this is related to hardware. Right. Next, I'm going to talk about some data types. Of course, we cannot cover all data types that we have in VHDL. While we progress, we introduce data types that we will need. So I'm going to talk about some, and they are grouped into categories, 3 categories: access, composite, and scalar. So I'm going to talk about some data types, so which we may need to use. Of course, one of them is very important, and we are going to use it. So we have character data type. Like in C, we have the char, so we have character here. We have Boolean, which could be false or true. If you declare a variable as Boolean, you can have values false or you can have value true. We have bit, which can be 0 or 1. And this is the most important type in VHDL, STD underscore logic. Why it is very important, and this is the one that you are going to use in the labs when you declare your inputs and outputs, because this is what it models really a pin or a wire. Because a wire, we say, okay, we can have 0 or 1. 0, let's say 0 volt, and the 1 is 5 volt. But you know, we may have inside the circuit or inside on a pin, we may have a value between 0 and 5 volts. So it's not 0, it's not 1. We may have a pin not connected at all. We might have a voltage that is very low, which is close to 0, voltage that is very high, which is close to 5. So we have other values, of course, in addition to 0 and 1. So this includes the bit, but it includes the other cases. So this is the best type for, to model a pin or a circuit, a wire. So it has other values. So you can declare a variable like that, std logic. You can give us the initial value 0. You can give us the initial value 1. You can give it the initial value x. So those are all possible values. So Z, which is not connected, high impedance, so weak signal. Even when you do simulation and when you check your output, you will get those outputs, those values as well. If it's 0 or 5, you will get 0, 1. But if it's not, you will get other values, different values, which shows that there is no output or there's something wrong or so on and so on. So for now, we will work with std logic underscore logic. This is the type that we use for our inputs and outputs. So as I said, I think one of the students asked me about the bus. So for example, if I have, let's say I want to do a ROM, and then I need to go to get the address bus. I'll call it A, and let's say I will have 4 here. So A, I need to declare it as a bus. I don't declare separate lines, A, B, C, D. No, we declare it as a bus, as a four lines. So what do we use? We use bit underscore vector, or of course, as I said, we will work with std logic. We work with this one, std underscore logic underscore vector. And then we specify how many lines we need. So for example, here, do you see here, I say 0 to 3. Counting from 0 to 3, how many lines? It's 4. So if I need 4, I need to put 0 to 3. Or you can do it this way, 3 down, as I wrote here, down to 0, and both will work. So counting from 0 to 3 or counting from 3 down to 0, you have four lines. So this is how we declare, for example, an address bus. We use std underscore logic underscore vector. There is the type as well, string, which is a character array, an array of characters. So basically, the std logic vector is an array of lines, right? So you can, do you know what is an array? Yeah, A5, for example. So you have an array of 5 elements. When you declare it integer A5, it's an array of 5 elements. If I use std logic vector, is an array of, let's say, 4 lines or 32 lines or whatever you declare. String, we have it, is an array of characters. So if you want an array of characters, you can, for example, constant. So I name it greetings. The type is string, and this is the value. And do you see, always for arrays, do you remember I told you if I want to give an initial value for A, I need to do it this way. A is equal, then I use double quotes, 0, 0, 0, 0. So it's double quotes because it's a vector. It's more than one line. Same for any array. Hello, for example, I just use double quotes. And the same, I think, for C++. Yeah, for string, you use double quote. Character, we use single quote, just one character, right? I can do A, X is equal A, character A. So if it's just one, we use single quote. If for multiple, we use, or for an array, we use double quotes. So which we apply the same here for one line and multiple lines. We use single quote and double quote when we work with bits, zeros and ones. Is this clear? I will do this and stop. We'll do this and stop. You know, we are running a little bit behind, so probably I will each time we may add, 5 minutes, 10 minutes, rather than to move a little bit faster, and then hopefully we will not need any extra sessions. We'll do this and then I will stop. I think we worked with this. We already used int, so port modes. When we declare a port, so we say A, and then we specify if it's integer in or out. You can have it in out as well. We have the in out. In some circuits, you will see this later on. Some pins need to be in out, can be considered as input and output. So they can you can work with them as inputs as output. You need to be careful, and the student, they do this mistake a lot. So when you declare an input, you cannot use the mod in signal on the left of an equation. You cannot assign a new value to input. So it's an input. We don't assign values to inputs, right? The value will come from external circuits or from external device or whatever. So we don't assign inputs to the value to the input. So for example, if I have A, let's say A and B are inputs, C is output. I cannot do A is equal B or A is equal C. This is wrong. So A cannot be in this side of the equation, right? We do C is equal A and B, for example. This is fine. So inputs are supposed to be in this side of the equation, and outputs are supposed to be in this side of the equation. So C cannot be here as well. I cannot do B is equal C. This is wrong. C cannot be in this side of the equation. But if it is in out, if it's declared as in out, it can go into both sides of the equation. If I put C here, C is in out, C can go to both sides of the equation. So you need to be careful. And of course, we do not declare, because if you declare a pin as in-out, it will use more resources. You know, when do you remember for the FPGA, we use the, you know, we said there is a, I forgot the name of the, what you will need for just one input is different from what you need for in-out. Those ones, the input-output cells. So you will use more cells if you want in-out. So if you don't need it to be in-out, you always specify it in or out. But you don't just say, oh, okay, let's put it in-out. I can work with both, so I don't have to worry about it. No, you should worry about it because you will be using resources that you may need for other things. So always make sure you use the right one, unless it has to be in-out. And we'll show you some examples later on when we do the tutorials, and we may face examples with in-out. Right, I will stop here. We'll do this exercise next session, and then we'll continue with, I think we have just a few remaining slides, and hopefully we'll start the next topic, inshallah. Right, do you have questions?
No, thank you, Doctor.
Okay, no problem. So if you don't have questions, then we'll talk to you next session, inshallah. It will be after, it's next week. So have a nice weekend, and talk to you next week, inshallah.
Thank you, Doctor.
So,
Doctor.
okay. Yes.
Doctor, I have a question. First lecture.
First lecture.
Yes.
Okay, that's fine. Yeah.
Can you share the screen for first lecture, please?
Yeah. Okay. But this was better for you to.
No, don't share it. Just let me say it for you. I think yes, A bar dot B plus B bar dot A, and you write equal A XOR B. How it comes like that?
Oh, you are asking about the XOR gate, yeah? I'm just trying to share the screen. Do you see the screen or you don't see it?
Yes, I see.
You see it, yeah?
Yeah.
So you are asking about the XOR, basically.
Yes.
This is how the XOR gate is defined. So the person who created those gates, they say, okay, this is XOR. A XOR B is equal to A dot B bar plus A bar dot B. This is your question, right?
Yes.
Yeah. So this is how the XOR gate is defined. So the person who created the XOR gate, this is his definition. This is how it works.
Mm.
So I don't know if you get my point or not.
Yes, I got it. Thank you.
So
I thought
it's not my definition. This is how the XOR gate is defined. Yeah.
okay. Thank you.
Okay, no problem.